This is section 7.8. It's titled Improper Integrals. Going back to Calc 1, Calc AB, the calculus you took last year, we are asked how do we evaluate just a basic definite integral. So first thing you always do is you integrate this. So you find the antiderivative of f of x. A lot of times we call that capital F of x. And we draw the a to b. And then we plug in b and plug in a. We get f of b minus f of a. The question we're looking at now is what if instead of b or instead of a, we either have positive infinity or negative infinity. So we want to know how much area do we have starting at a and going all the way up to infinity. And a lot of times, my graph looks like this, and I have a right here, and it continues to go up. A lot of times we're going to have an infinite amount of area under the curve, but not necessarily always. If we have a horizontal asymptote at y equals 0 in the graph, looks like that, and it gets infinitely close to 0, it's possible that we could have a finite amount of area that we need to find as it goes up to infinity, or as it goes down to negative infinity. So we need to take a look at what we need to do if we have an infinity up there or down here. That is one type of improper integral, is if you have an infinity in one or both of your bounds. And we're going to start out the same way. We're going to integrate f of x, and we can still write it as a and infinity here. But we can't evaluate f of infinity. F of infinity, it isn't a thing. We can't plug infinity in for f. So what we're doing instead is we're evaluating f of b minus f of a, but we want b to approach infinity. So we're evaluating the limit as b approaches infinity of f of b minus f of a. And the same thing here. We would integrate, we would do f of b minus f of a, but we don't actually have an a value to plug in. We have negative infinity to plug in. So we are evaluating the limit as x approaches negative infinity. A couple things we need to keep in mind. First of all, you have to have a continuous function on the interval. So from a to infinity, you can't have any, like a jump. Or more importantly, you can't have a vertical asymptote. That'd be the big one. And we'll talk about what to do if you do have a vertical asymptote somewhere on the interval. So if it looks something like that, you can't just consider what's happening at the endpoints in that case. Also, if the limit as b approaches infinity does not exist, that tells you that the area is an infinite amount. So the integral diverges is what we say. All right, let's take a look at one here. So this asks us to evaluate the integral from 2 to infinity of 3 over x to the 5th dx. 3 over x to the 5th dx. So 2 to infinity, 3x to the negative 5th. Add 1 to the exponent. Divide by that same thing. So we have negative 3 over 4x to the 4th. So plug in infinity. We can't really actually plug in infinity. So we're going to do the limit as x approaches infinity of negative 3 over 4x to the 4th minus plug in 2. 2 is a number, so we don't have to worry about the limit as x approaches it. 2 to the 4th is 16. Real quick reminder of the rules on evaluating the limit as x goes to infinity. If the degree is bigger on the bottom than it is on the top, which is the case here, then the limit goes to 0. which kind of makes sense. If you were to plug in infinity, the bottom would be really, really, really big. So 3 divided by an infinitely big number is 0. If the degrees are the same, if it looked like this, you divide the leading coefficients, -3 divided by 4. And if it's bigger on the top than it is on the bottom, then the limit does not exist, so the integral would diverge in that case. But in this case, when I plug in infinity, the degree is bigger on the bottom, so it's 0. Minus, minus, I changed to plus there. So we've got 3 over 64, which is our answer. Example 2, the integral from 0 to infinity of e to the negative x dx. I'm going to use substitute here. So we need negative dx, there's du. You can change your bounds if you'd like. I'm just going to change everything back to x's after I integrate. Might be easier in this case. So the integral of e to the u is e to the u. So I have e to the negative x from 0 to infinity. You are welcome to change your bounds and work out the same. We're plugging in infinity, which we technically cannot do. We're evaluating the limit as x goes to infinity. Plug in 0 gives me e to the 0, so I have -1. Minus, minus, again, it's plus. E to the x, or e to the negative x, I'd move it down to the bottom. And this one's not really a polynomial over a polynomial. So you can't really use the degree rule, but again, think about if I plug in infinity here, I have e to the infinity. On the bottom, I have something infinitely big. 1 divided by that goes to 0, plus 1. The area under that curve is 1. Integral from 4 to infinity of 4 over root x dx. Integrate, add 1 to the exponent, divide by that. Dividing by 1/2 is the same as multiplying times 2. Plugging in infinity. Plug in 4. The limit as x goes to infinity of 8 times square root of x. Notice the degree is bigger on the top than it is on the bottom. That's x to the 0. So this does not exist. Therefore, we say that that integral diverges. Integral from 0 to infinity of e to the x over 1 plus e to the x dx. We need to use substitute. We're going to make u equal to 1 plus e to the x. So my du is e to the x dx, which is right here. So I get 1 over u du. We didn't change the bounds last time, so I'm going to this time. If I plug in 0, I get 1 plus 1. I think that's 2. And if I plug in infinity, I get 1 plus e to the infinity. Well, e to the infinity is just infinity. Plus 1 is still just infinity. integral of 1 over u is natural log. Plugging in infinity, I have the limit as, technically, I guess that's b. You could put u, it doesn't matter. The limit as b goes to infinity of natural log of b minus natural log of 2. The natural log of an infinitely big number does go to infinity, so this one also diverges. If you look at the natural log graph. So as x is getting bigger, this gets bigger and bigger and bigger and bigger, and it never comes back down. So as it gets infinitely big, the y value also gets infinitely big. Example 5. Notice that both of these have a vertical asymptote at x equals 0. If I plug in 0 for x, I'm getting undefined here, 5 divided by 0. This one also has a vertical asymptote at x equals 0. So we can integrate. Add 1, divide by that. From 0 to 9. Plug in 9. Plug in 0 gives me 5 over 0. This is undefined, therefore the limit does not exist, therefore this diverges. So when you have this vertical asymptote here, really what you're doing, you can just plug it in, that's not a big deal. But really what we're doing is we're evaluating the limit as, I guess that's a goes to 0 of -5 over 2a squared. And then you directly substitute. You can just plug the 0 in instead of writing this step. That's no big deal. But once you see you're dividing by 0 there, hopefully we recognize that it diverges. This one, if you look at the two graphs, they look very similar. Both of them kind of go down. Both of them have a horizontal asymptote. But notice this one, when we do it, let's see here, 0 to 9 of 5x to the -1/2 dx. When I add 1 to the exponent, it's not negative this time. So now when I plug in 0, I'm actually going to be okay. So add 1 to the exponent, divide by 1/2. If I plug in 9, 1/2 is the same as square root. Plug in 0, no longer gives me undefined. So this one has a finite amount of area. So even though they both have that vertical asymptote there at 9's over here somewhere, both of them have a vertical asymptote here at 0. One of them, this one here, has an infinite amount of area under there, and then this one has a finite amount of area. Example 6 asks us to integrate from 0 to 9 of 4 over the cube root of x minus 1. Ones like these, it's always real important to check to see if you have a vertical asymptote. This one, our vertical asymptote, is at x equals 1, which is right in the middle of our bounds here. If that's the case, you have to split this into two separate integrals. You have to integrate from 0 to 1. and then you have to integrate from 1 to 9. Sometimes if you don't do that, it'll turn out okay, and you'll get the same answer, but sometimes you'll get the incorrect answer if you ignore and don't split this into 2. So we need to u substitute. U equals x minus 1, du is dx. So I get 4 over the cube root of u. Change your bounds. If I plug in 0, I get -1. If I plug in 1, I get 0. I need to integrate. Haven't done that yet. Add 1 to the exponent. Divide by 2/3. Plug in 0 gives me 0. Plug in -1. Cube root is still -1. Squared is +1 times 6. So integrating that part gives me -6. And then I need to do this part here. Most of this work, notice, is going to be the same. This will be the same. This will be the same. This, my bounds will be different. But the integrand is the same. I still get 6u to the 2/3. We do need to change our bounds. If I plug in 1, I get 0. And if I plug in 9, I get 8. Plugging in 8, cube root is 2, squared is 4, times 6 is 24. And plugging in 0 gives me 0. $18 is correct. And I believe on this one, if we had ignored the vertical asymptote and just integrated from 0 to 9, that's what you would have gotten on this one. Sometimes, though, it'll spit out a number if you do it without splitting it up, when in actuality it diverges, which I think might happen. So very similar problem here, but we're squaring instead. So again, u equals x minus 1, and du is dx. We do need to split this up. We have a vertical asymptote at 1. So 0 to 1. And 1 to 9. So we get 4u to the -2nd. Change bounds. Integrate. And when I plug in 0 here, notice I get 4 divided by 0, so this does not exist. So our integral diverges. Notice if you had not split it into 2 separate ones, you would not have this 0 to plug in. You would just plug in the -1, and over here you would plug in the 8, because we changed our bounds. So you would have gotten a number if you had just done it without splitting it up. So it's important to always split it into 2 integrals if you have a vertical asymptote that is somewhere in between the 2 bounds. If it's right on the edge, like this one here, the 0 was the vertical asymptote, that's okay. If it's not on the integral at all, or the interval at all, you don't need to worry about it. But if it's in between there, you do need to split it up. I'm not going to do that one. Last one, you give this one a try. It's right off an old AP exam. You try this one. Pause the video, try it, and then I'll show you how it's done. So we're going to make u equal to x cubed plus 2 up to 3. So du is 3x squared dx. So we get 1/3 the integral of 1 over u squared du. I'm going to change my bounds. Plugging in 1 gives me 3, and plugging in infinity gives me infinity. I'm going to change that so it says u to the negative second. Integrating. Don't forget your 1/3. So 1/3 times negative 1 over u. So I get negative 1 over 3u from 3 to infinity. Plugging in infinity, which I technically can't do, we are evaluating the limit as b goes to infinity of negative 1 over 3b. And I'm also plugging in 3. I have negative 1 over infinity, that's going to go to 0 plus 1/9. I get b 1/9. So that is improper integrals. If you're having questions on any of this stuff, let me know.